Hey guys, so this is our video going over the practice problems that are in the lecture. As pointed out in the lecture, instead of splitting this up into finding t-statistics for the b-values and for these three problems and then just a confidence interval for this one, we're just going to find the t-statistic for all four of these as well as the confidence interval that would exist in a population for all of these. Okay, and again, our evaluation is of B, and remember B is going to be representing the slope of the regression line. Specifically for these examples, we're calculating for bivariate regressions, so it'll represent the slope of the bivariate regression line in terms of representing what a given relationship would be in terms of the units of measurement for the independent and dependent variables. Okay, so in this spreadsheet, you can do something similar, but I've kind of organized what my known information is, right? So I know my b values, my standard error of the slope, which is b, as well as my sample size and the level of confidence I'm operating at. Up here is just a reiteration of some conceptual stuff that has been covered in the lecture, as well as the activity and the flowchart videos. So when we're looking at the significance of a B coefficient, okay, which is kind of the purpose of this first section, right, we're considering is a B value or is a relationship between a given independent variable and dependent variable significant enough for that independent variable to be considered a good predictor for the dependent variable. Now, good is used a little bit loosely because we're only using one independent variable in a bivariate regression, so we're just saying, is it sufficient enough to be able to predict a good chunk of the dependent variable? So in this case, our null hypothesis for, since we're testing, do we have significance or not, right? The null hypothesis for that P and alpha evaluation is that the value of B for a given independent variable does not significantly contribute to the prediction of a given dependent variable. Now remember, if we're looking at regressions create equations in order to predict values of a dependent variable based on measured values of an independent variable. So we're kind of working off of like the B coefficient that would be given in a regression line, and we're saying, is that significant enough to predict whatever our dependent variable is? Okay, so the first unknown that we need to find is the degrees of freedom. So remember, degrees of freedom for a regression is going to be n, or the sample size, minus however many independent variables we have. In this situation, if it's a bivariate regression, there's one independent variable, one dependent variable. Therefore, degrees of freedom will be calculated by looking at n minus 1, which is our independent variable, right? Or 1 representing our single independent variable. So n, right, in our degrees of freedom, we're just saying n minus 1, and that'll be the same for each of these here. Okay. From here, we calculate our t-statistic. So then we have to find our t-statistic. Now remember, in the lecture, we distinguish t from t-scores associated with critical values. Okay, so t is going to be calculated by taking b divided by the standard error of b. So this one is a pretty simple calculation for us to do in Excel, where we're just going to create cell references and divide accordingly. I'm going to make all of these to the second decimal place. Okay. From here, CV, or the critical value, is what we need in order to be significant at a given level of confidence. So this is where our t-table or t-distribution comes in. And this is where our levels of confidence will come in. So on the t-distribution, you have a cumulative probability that is listed up top. So that's one way that you can find your level of confidence per se. But I preferred to use the actual confidence levels down here to look up my critical values. You can also go off of the one or two-tailed values in which, like say we're looking at a 95% level of confidence, two tails, the sum, right, would be 0.05 versus if you looked in one tail of a two-tailed test, it would be 0.25. So again, I think the top part is a little bit more confusing. So I prefer to look at the confidence level part at the bottom to find my critical value. So in the first example, we have a degrees of freedom of 21, which is what we will look up in this column over here. And then we have a level of confidence defined as 95%. So we use these two bits of information to find the critical value that we would need in order to prove significance. So starting at 95 and lining that up with degrees of freedom of 21, we see that there is a critical value of 2.08. Okay. So then when we're determining do we have significance or not, recall that when t is greater than a given critical value, we have significance. Okay, so if we're looking at this, 2.00 is less than 2.08. Therefore, p is going to end up being greater than 0.05, meaning we have no significance, or the b value is not significant. Okay, try to write this as many ways as possible so it clicks with you guys. Okay, if we look at the next example, again using the level of confidence and a given degrees of freedom, we're going to look up 95% on our confidence level area, and then our degrees of freedom is 40. Now when it comes to these larger values, past 30 and 40 degrees of freedom, usually the difference between, say, like 40 and 41 is not going to be that different. So what you'll do in these instances is you'll just pick the value in the degrees of freedom that's closest to your actual degrees of freedom. So in this case, we have 41, we would choose 40. Okay, so if we line that up with 95%, we get a critical value of 2.021. So we can evaluate, does our t statistic that we calculated using information from our sample, is that larger than the value we need to prove significance? In this case, we do, right? 2.03 is greater than 2.021. So in this case, our p-value would be less than 0.05, right? We're saying less than 0.05 because that's the alpha value that's associated with a 95% level of confidence. So in this case, we do have significance. Okay. Similarly, for our next example, we calculated a t-statistic of 3.13, and we need to find the critical value that would mean that we have a significance of the b coefficient, right, at 99%, with degrees of freedom of 11. So if we go to 99% on our level of confidence area, and we go up to 11, we'll notice we need 3.106 to prove significance. When we evaluate our t statistic to our critical value, t is greater than our critical value, so we would say p is less than 0.05, therefore we have significance. Okay, so one thing I want to point out before we do the last example is that you'll notice as you increase your interval size, the actual size of the t-statistic or the size of the critical value is going to increase. Okay, and also as you go up the table, right, or your degrees of freedom are smaller, indicating you have a smaller sample size, also the larger the critical value is. So this is a good example of why a larger sample size is better, because one, you have a more representative subset of the population, but also the area in which you're trying, or your area of rejection, is technically going to be smaller, right? So the size of the difference that you're proving, or the size of the relationship that you're proving, is going to end up being smaller if you have more people that you're considering in your calculations. Okay, so for our last example, if we're using a 95% level of confidence and we have degrees of freedom of 24, we can look up what the critical value would be to prove significance. So 95, 24, right, would give us a critical value of 2.064. Okay. So when we compare this, t is in fact greater than our critical value. Therefore, this would be another example where p is greater than 0.05. Therefore, we have significance. And I just realized this was a 99, so p would actually be 0.01 in this scenario. Okay. There's other examples where I may give you this information over here, but I don't tell you what level of confidence you're trying to prove, right? So let's take our second one, for example. This is completely arbitrary choice. But let's say that we calculated a t-statistic of 2.03, and we wanted to see what the highest level of confidence that we could use in order to prove significance, right? So let's say we start, or we kind of stick to our main levels of confidence, which are 90, 95, and 99. So if we look at 90, right, our degrees of freedom was 41. So we'll stick with 40 for this example. Okay. At 90% level of confidence, right, our critical value would be 1.684. So we know if we're looking at our t-statistic, which is 2.03, right, that is greater than the critical value on the table. So then we could jump and say, all right, well, we know p would be less than 0.10, so is it less than 0.05, right? And then you evaluate your critical value at the next highest level of confidence. Again, this would mean we're making our alpha level smaller. So if that's the case, we are basically kind of decreasing the size of the region of rejection, or decreasing the amount of error we're willing to accept. So we already proved that p is significant, right? Or p is less, or not p is significant, our b is significant, right? With a p less than 0.05 for a 95% confidence interval. So then we could take it a step further and say, well, does this still ring true at a 99% level of confidence? Well, if we look at the critical value at 99%, it's 2.704. So in this case, t would be less than the critical value on the table. So we would say the highest level of significance that we can find is where p is less than 0.05, but p would be greater than 0.01, if that kind of makes sense, right? We could do the same thing for our example for number 3, right? So t is the calculated value, and we're just trying to say at what level of confidence do we have significance. Okay, so we could look at the table starting at 90%, right? This being our lowest level of confidence. Okay, and we can see t is greater than the critical value at 90%, t is greater than the critical value at 95%, and t is also greater than the value at 99%, right? So if you can make it to 99, where your t is greater than 99, then you use that smallest alpha level or the largest confidence level that you can, okay? In situations where your critical value is less than a critical value at 90%, then you would use 90% as your kind of base point, where you would say P was not significant at a 90% level of confidence. That indicates it's also not significant at 95 and 99. Okay, so what do we do with this information? We can then calculate our confidence intervals. Okay, so we've got everything we need to calculate these now. Confidence intervals are going to be B, for at least the lower bound, it's going to be B minus the standard error of B times the critical value T, or we say TCV in the notes, but this is really the critical value that would exist at a given level of confidence. So basically you're saying this confidence interval or this lower bound is going to be based off of whatever the critical value that exists for given degrees of freedom and level of confidence. Okay, so in order for you to calculate the confidence interval, you have to have already found what the critical value was, or at least you need to know the degrees of freedom and the level of confidence in order to find the critical value. Okay, so lower end is going to be minus, upper end is going to be plus. Okay, so we can plug and chug pretty easily in Excel, where we say B minus standard error times the critical value that exists at a given degrees of freedom and level of confidence. Okay. If we copy this formula and change that minus to a plus, we now have our upper confidence interval, right? And then this is just going to be, whoops, I can't paste that, never mind. This is just going to reflect the values that we got in a bracket format. Okay, so this would be how we actually type out our confidence interval. Oh, and I need to get rid of that. Okay. So the same thing could go for these other intervals, right? Where you're just taking, plug and chug these certain values, right? Lower end is going to be minus, upper end is plus, and we end up figuring out what our intervals are. So for the second one, let's say we're making all of these to the second decimal place. Oh, we can do third, that's fine. Okay, so this one would be 0.003 to 3.197. This one would be 0.912 to 299.088. And 78.72 to 161.28. Okay, so I just want to reiterate what the confidence interval actually means. One second. Alright, so you're probably thinking, well, if the confidence interval is representing the true B, shouldn't B, if it's a relationship, be between 0 and 1? Well, you have to remember B is going to be in the units of the independent variable. So basically it's saying for a given change in X, we get a single unit change in y, right? Or actually backwards. If you think of slope, right, or m, it's rise over run, which is basically the change in y divided by the change in x, right? So if we have a slope of, let's use 1.6, right? We assume 1.6 is over 1 when we see a whole number. So this would actually indicate for every change in, we'll get 1.6 change in y for every 1 unit change in x, okay? If we wanted to use an example, let's say of school debt, right? And we say x in this case is years, okay, in school, and we're gonna say the rate of change in x maybe is or let's not say that. Maybe let's say for every year in school you accumulate $8,000 of debt. Sure. Okay. So we'll say this is the cost, or maybe we'll call it annual cost. Okay. If we're building an equation and we want to know what the total cost is, which will be represented by y, hopefully you're following my logic here, right? We build an equation and we say y is equal to, right? Each year we're in school, it's going to cost us $8,000, right? Times however many years we're in. So that would be x, right? And maybe let's say when you start school, it's a $500 down payment, right? For just entering it, call it an enrollment fee. So you have this one-time enrollment fee, which is acting like your y-intercept, right? And then each year, which x is representing the number of years, you're accumulating $8,000. So when we look at b, right, it's in the units of what we're actually trying to predict. So b in this case is 8,000, right? That's the slope, okay? So for every 1 unit change in x, or for every year we're in school, we're accumulating $8,000, which is going to represent the change in y, right? So b is representing how much change we're going to see in our dependent variable based on a 1 unit change in our x variable. Okay, so all we're evaluating is that rate of change, or is that relationship going to be significant enough that we're significantly contributing to the prediction of whatever the dependent variable is. Okay, and that's what this significance column is looking for. And this confidence interval is going to tell us what b would be, right? What b should exist as in a true population. Okay, so hopefully that helps clear up some of this information.